Okay, welcome back. We're on page 384 talking about multitasking. And the closest analogy in the network world is that statistical multiplexing where I've got several conversations going on over the cable at the same time. Same thing, is I just have multiple things going on. Now, just like statistical multiplexing, really, there's only one stream of data. It's just been divvied up by different customers. Well, it's the same thing here. It may look like that when I'm dragging this window around, it may look like that I'm actually running two programs simultaneously. Well, it's just done so fast. It just looks like it's doing it. It really is running this application and then that application, one right after the other. But it does it so fast that you can't tell. Okay. So, the OS, the operating system, is responsible for what's managing resources. And so the next question to ask is resource. What resources are you talking about? So that's kind of important. One of the resources that we're talking about is running processes. So this basically tells me all of the processes that are currently running on the system. Now, what is a process? Well, it's things that are currently running. It could be things that you directly invoked. If so, that would be on this list. So the things that I have directly invoked myself as a human is I've got this Windows Explorer guy up pointing to Chapter 12. I've got an image viewer up pointing to that, and I've got a website up pointing to the university's website. That's what I've got going. But processes are a lot more than that. Processes include those things plus all the things that the operating system is going on that you don't necessarily see and you didn't directly invoke. Okay, so it's applications, services, all these components of the operating system like what we're seeing here, plus all of the data associated. So this process basically has a chunk of memory associated with it. So this Explorer right here, which is the one that has probably that one right there, has a pretty good chunk of memory being used for it. And this Internet Explorer guy has another good chunk of memory being used for it. So not only does this process contain the running application, but all the running application's current data that it's using. Cool. All right. Each process essentially has a particular state. And the state meaning where is it in the big picture? So here are the states. I either have a brand new process that I just created and it jumps in, and so it says, okay, I'm ready. And then if there's nothing else going on the machine, it could probably transition to running. And then if it's after you're done, then it goes to termination. So this is the normal kind of a loop. Now, let's say I'm running Notepad. So I go here and I go to Notepad. Now, what is Notepad running? Well, of course it is. It's right there. I can see it on the screen. But what is it actually doing right this second? What is it doing? What is it doing? Absolutely nothing, because it's waiting for me. So down here, there's a thing called waiting, where I go in here and I say, I'm waiting for some human to hit a key on the keyboard. And so it just sits there and waits. And then as soon as I hit the key on the keyboard, it goes, aha! I saw a keystroke. Let me go process that. And then it goes to ready. And it goes back to running and wait. So this is typical of one of those scenarios where there's an awful lot of human intervention, like, Microsoft Word or Notepad or, whatever it is. That, yes, you'll go through this little routine where it waits and then it's ready, and then it waits and it's ready, and it waits and it's ready over and over and over and over and over. Okay. Now, the good part about that is, while it's in the waiting state, like right this very second, it's waiting. If my machine was running low on memory, and the machine says, oh man, I got way too many of these processes in memory, and I gotta shed some of them because I got some really important things I need to do. I'm gonna look at all the running processes, and I'm gonna take a few of them, and I'm gonna temporarily store them off onto my hard drive to get them out of memory. And then if anyone needs it, I'll just very quickly go get that and replace it. Now, which one of these applications do I want to do that to? Well, why don't I do it to the one that's currently not doing anything at all? Does that make sense? Find the ones that are in the wait state and put them off the disk to free up memory for other applications. Okay. So that's the significance of the waiting state. It makes it more eligible for being tucked away if you're in a memory constraint. Anyway, that whole thing I just described is called swapping. I have all these processes running in memory. By the way, I should have another one here. See, got Notepad. I have all these processes running, and I'm running out. Am I running out of memory? Nah, I'm doing pretty good. I'm not. I got 2 gig of RAM, and I'm just under a gig being used. Okay. So, bottom line is, if I was running out, if I only have 2 gig of memory, can I have 3 gigs worth of memory of applications in use? Well, the answer to that question is not really, but I can make it look like you can by taking these things and swapping them out and then bringing them back when they need them over again. It is not incredibly fast to take a running application, pause it, throw it out on a hard drive, and then come back and get it and pull it back. That's an expensive operation, but hey, if you're running out of memory, you don't have much of a choice. Okay, cool. So that's swapping. I don't have enough memory, so I swap an entire process out and then do whatever I need to do, and hopefully the memory constraint will be better, and then I can bring that guy back. Okay, cool. So just to keep drilling down, so now we know about processes. There's actually something underneath processes that's called threads. I know this is a little esoteric, but just bear with me. So a thread is like the smallest unit of measure that you can do that the machine can actually operate. Have you ever noticed, for example, if you start Microsoft Word or one of those guys, so I'm going to go here and fire up Microsoft Word. There's see a little splash screen there? The splash screen fired up as the application was loading. Okay? Now that's a good thing, because what that's basically telling me is there were 2 threads running. One thread was the splash screen, and while that thread is running, it's going to get the files and bringing them up and starting Microsoft Word. Because it could have taken, this was pretty fast, but it could have taken, 5 or 6 seconds to launch Microsoft Word on your computer. And during that time, that little splash screen is up on the screen saying, be patient, we're about to load, just hang on. That's what that little splash screen is for. And that's done not with 2 separate processes. It's done with 2 separate threads. So I launch Microsoft Word, a single process, and it creates 2 threads. A splash screen thread that says, hang on, while I'm working on it, don't get impatient. And the other thread is very quickly trying to pull all the things together and pull it all and actually launch the application. So multiple threads. Okay, so one more time just to drill home the point. A single process can have multiple threads. Okay, cool. Creating new processes, the things that show up here, that's kind of expensive for the computer. It has to do a lot. All the state stuff we just talked about, it has to do all this stuff. It has to load it and get in the priority queue and listen for input and all the rest. It's got a lot of things to do. And it's kind of expensive to create a new process. However, it is not expensive for a process to create new threads. So programmers know this, and so they choose to have single processes with multiple threads. Okay, cool. So let's just look at like web server. I don't have a web server up here, but there's an example in the book where they show the console up for a web server. And so web server, and in this particular case, it was configured, looking at the book, it was configured to have 25 threads per CPU installed. So for example, in this particular case, this machine has 2 CPUs, and therefore it would have up to 50 threads. So the way it was configured there is I could have 50 different people coming in hitting my website. If the 51st one came in, it would say, sorry dude, go away. So one single process creating 25 CPUs per 25 threads per CPU. And of course, you'd have to know how many CPUs you had in your machine to be able to answer that question. But hey, which is, by the way, it's kind of sort of here. If you go back to this guy, and you can basically, how many stacks are there in this little diagram? How's that? So I have 2 little stacks, so I have 2 CPUs. Okay. So, likewise, let's say I have a web browser. So I have a web browser up, and when this page first loaded, the very first time, this was a piece of graphic here, and there's some graphic behind here, and so is this how it worked? It pulled up the web page, and then went and got the first graphic, and then went and got the second one, and then the third one. Is that the way that worked? No. It pulled up the page and loaded all the graphics simultaneously. Well, as near as simultaneous as you can on a computer. It fired off separate threads to go get this logo, and a separate thread to go get this background, a separate thread to go get this text, and all the rest of the graphics, and separate, graphics for this, and all the things in here, all done on separate threads. So it made your website, your web page, look like it was doing a heck of a lot of stuff, and it was very fast. We like fast things, don't we? Okay, good. So, web browsers downloading text and graphics simultaneously, that's done with threads on a single process. I think we beat that to death. So, the operating system is the one that's responsible for the starting and the ready and the running and the wait and the terminating. It has to do all that, right? It also is responsible for handling deadlocks. Let's say, for example, that I have 2 applications up there, and both of them are trying to get to the speaker at the same time. Well, how does the operating system handle that? Does it just allow both of them to blast at the same time? It could. What about input device? Let's say I have 2 applications that are trying to read where my mouse is simultaneously. Is that allowed? Not really. What if we're both waiting for a particular device to show up? I'm trying to open a device, and you're trying to do the close on the very same device at the same time. So the operating system has to handle the beginning, starting, and what's called a deadlock condition, where we're both competing for the same thing, but we're asking for different things. All right. That's what that is. It's also responsible for sharing data from different running processes. So the CPU operating system part does that. The next resource that we're going to talk about is on page 390, and that's memory. Okay, that kind of makes sense. And so memory on a computer, I'm going to go back to this little guy. Oh, actually, we can go here. So memory in this case is, this is sticks of RAM that's installed in your machine. Random access memory, you've probably heard those terms, at least I hope. So this is the amount of memory you have on your machine. Cool. It's used for storage of the things that are currently running. Okay, that kind of makes sense. And we call this primary storage. I know that's a weird term, but a more appropriate term would be called transient storage. Transient mean when the power goes off, everything that's in that storage goes away. Okay, so it's transient. Contrast that with hard drives, which would be considered secondary storage. When you turn the power off on them, if you did an orderly shutdown, if you turn the power off on them, when you turn them back on, all your information is still there. So secondary storage would be things like floppy disks and CD-ROMs and USB flash drives and, hard drives and solid-state drives and all the things that you're familiar with. And there's very few things in the category of primary, because primary storage is just, just memory. That's it. It could be built into your phone. It could be built into your tablet. It could be little devices that you install on your own computer. Okay. This is a good place to stop for the 15-minute mark. We'll pick this thing up again in just a few.